Welcome back. Let's talk about stacks and queues. So I'll present the basic ideas and then we'll look at some classic algorithms that use a stack and a queue. So a stack is this kind of thing right here. You've got a push operation for putting data on the stack and then a pop operation for removing the data. So you're only accessing one side of the stack. And sometimes that's called a LIFO list for last in, first out. I personally don't really like that term. I think the term last and first are kind of relative. And when you start thinking about the algorithm that's using the stack, it gets a little confusing. But this is the classic definition or the classic name for these things. Sometimes they're also called a push down store, which I kind of like better. But anyway, so here's what the functions might look like in a C-like language. So for pushing, the data is the argument, and then for popping, the data is the return value. So the data is stacked up because you're only accessing one side. It's very much like a stack of dishes, let's say, in your pantry, in the kitchen. You might stack up your plates or something. So you're always accessing the plate off the top of the stack. At least that's what I do in my house. I very rarely dig into the stack and get something from, that's not the first one. That's just what I do. Probably most people, I would guess. Okay, so that's the idea of a stack. So the next structure here is a queue, spelled this way, sometimes spelled without the UE. But anyway, this is called a first in, first out store. And in England, they use the term queue for lining up. They say queue up at the store. So, that's the best way to think of it. Is it's like a line at the store. You get in at one end, and then you wait, and you work your way through the queue, through the line that is to say, and then you're dequeued at the end. So the access functions are queue, where you're putting data into the queue, and then dequeue, where you're removing data. All right, so these guys have certain characteristics that lend themselves to certain algorithms. So remember, we talked about containers before. We talked about the idea of an algorithm that uses a container of some kind. So this could be a stack down in here, and you have some algorithm that's using the stack, and this line right here is the interface. That is, in this case, it would be push and pop. So basically the sum algorithm is calling push and pop operations on this stack. We're going to look at a couple of those, and then we can get a little fancier, and we could have algorithms that utilize both of these things. You could have a stack down in here and a queue over here, and this guy, whatever, the up in here could be doing loops and whatnot, and calling these push and pop operations, or calling queue and dequeue. That's what we're going to look at. This is a good way to think about modularization or abstraction or containers. Those are all kind of the same thing, and object-oriented languages support this kind of containerization with classes and things like that. All right. Okay, so let's look at a couple of, in general, what can you do with these guys? Well, so stacks are used by procedural programming languages like C and C++, and basically most languages are like that. When you call a function, you need to be able to find your way back, right? You can call a function, and then that function calls a function, it calls a function, calls a function, and all of that path of function calls is pushed onto the stack, which is a section of memory. And this is kind of built into the architecture of processors now. There's actually a stack, somewhere on the chip that is is used in conjunction with the code that's executing. So what I'm trying to say is that this idea of a stack and using it to keep track of function calls is so integral into how modern programming languages work, that it's all supported by the hardware itself. Okay, so a stack is used to keep track of your function call path, right, and the local variables as well. And we're going to look at some classic algorithms that are used to convert string expressions, yeah, we'll look at that. And okay, and we looked at recursion earlier in the class. We looked at the maze algorithm and the Queen's algorithm and Hanoi and some others. Those were all recursive functions. And if you remember, I mentioned in recursive algorithms, when I was talking about recursive algorithms, I mentioned that generally speaking, you can convert any recursive function into a iterative version and vice versa. And one way to do that is to utilize a stack. So what I'm saying is you can convert a recursive function into an iterative function by using a stack, in the loop, or that is, you'll have a loop, you'll have an iterative loop, and it will be accessing a stack, pushing and popping operation onto an explicit stack, as opposed to using recursion, where with recursion you sort of have an implicit stack. You're using the stack that's built into the function calling mechanism. Okay, so there's a relationship between recursion and iteration, and you can convert back and forth between the two, and a stack is involved in that. All right, for queues, some examples of using queues they're used in the operating system to manage processes and resources, and that what happens in the operating system is kind of similar to what happens in lots of programs, including games. Many games are queuing simulations, where you have a bunch of data in queues, and the data moves back and forth. Like let's say, for example, you wanted to make a theme park game. Like there was one I was playing for a while, something with roller coasters, Roller Coaster Tycoon or some junk. So you have these roller coasters, and each one is really a queue. And then you have a restaurant. So you've got coaster, and then you've got the merry-go-round, and you've got a restaurant. And each one of these is a queue with people. They go into the restaurant, and then they eat, and they kind of work their way through the queue, and then at some point they'll come out and they'll get in another queue for the next ride. So you can vary the size of these queues, how many people they support, their speed, that kind of thing, and that's the whole game. You want to keep people moving around. Okay, so queues are used in certain kinds of game programs, as well as this is what the operating system is doing. It's managing processes that are in different states. You can take several classes on just how to write operating systems at the junior level in some colleges. Okay, so let's look at some specific applications of stacks and queues. All right, so let's look at some classical stack and queue algorithms. So first one we got is reversing a word using a stack. So let's say I had a foobar. I could read each one of these guys and push it onto a stack. So F. So I'd read these guys like that. I'd push F on there, and keep going around in here. O O B A R, right? Just by pushing in a loop. Then after that loop's done, you go to this guy where you're just popping, and they're going to come off in opposite order. They're going to come R A B U U F, raboof. Okay, just a simple algorithm using a stack that will reverse the characters. So here's another one. This one here will check if parentheses are balanced. For example, let's say you had 2 plus 2 times 3. So if I have a closing paren here, I need another one here. That's what we mean by balance. For every left paren, I have to have a matching right paren. Otherwise, there's something wrong with the expression. So this is used by compilers when they translate your code into assembly code, right? The compiler will perform many checks, one of which is just checking to see if your parentheses balance. And if they don't, it'll spit out an error down at the bottom of the compiler error something, something, something unintelligible with, and then you have to go back to this line and figure out that you're, what you did wrong. So this one here, let's see, you read these symbols in, they're characters, parentheses, just a character. You read it in, and if it's a left paren, you push it. So here's our stack, so we'll push that guy. And if it's a right, well, so then we'll read another one and push it. Then we'll read this guy, and we'll read all of these guys and do nothing. But now we read, and it's a right paren. So the stack is not empty, so we pop it. So you could redraw the stack like that. Then you come around until you read this guy, and it's not empty, so you pop it, and then the stack should be empty if it's good. But if I had an extra one of these parens, then the stack would not be empty, right? Or if I didn't have enough of these right parens, then I wouldn't do enough pops, and the stack would not be empty. So you could try executing this with some incorrect, some unbalanced parentheses, and see what happens. Okay, so we've written a couple of algorithms that are utilizing stacks to perform various operations. Let's look at another one. So here's a palindrome. This guy recognizes palindromes. Oops. So a palindrome is a word that reads the same forward as it does backwards, like radar is the classic example. Or if you're Hannah Montana, which always I think is humorous. I'm not sure why, but this one's a palindrome, and this one's not. So yes, no. Okay. So let's check radar. Let's check radar and see if radar is a palindrome, which it should be. So this one's using a stack and a queue. So here's our stack, and here's our queue, and we'll check radar. So so we read in a character and push it. So we read in R, and we enqueue it. So we're going to come in on this side, so it'll go to the front of the line. Okay, and then we read the next one, push it, and enqueue it. And we're just going to run through this guy pushing and enqueuing. So this guy will come up like this, and this guy will come in like that. Then, while the stack is not empty and the queue is not empty, we check if the data we've popped and the data we've dequeued are the same, and they should be the same, right? So you pop off the R and the R, they're the same. The A and the A, they're the same. The D and the D, they're the same. A and the A, the R and the R. So it's a palindrome. If you did Montana, it would come in. Let's see. Montana would come in this way. Then you'd pop off the A and the A, and it would fail right here. Okay, so a little classic algorithm to utilize a stack and a queue. What was the time complexity of all three of these guys? Well, we need to define n. So let's define n as the length of the string for each one of these guys. Then each one of these guys had to scan the entire string. So you're stuck with that. If you define the size of the problem n as the number of elements in the string, well, all of these are going to have big O of n. All right, moving right along. So this is a pretty good classic algorithm here to convert an infix expression to a postfix expression. So infix is this kind of thing, like 2 times 2 infix. So we have operands and operators. So 2 is an operand, and the multiply sign is an operator. Okay, so operator and operand. So this is what we call a binary operation because there's 2 operands. That's where the word binary, that's what it means, is that there's 2 operands. That's what it means in this context. So we're not talking about binary numbers here. We're talking about a different use of the word binary. So we have 2 operands and then 1 operator here. So this is multiplication is a binary operation because it has 2 operands. So this is the typical way of representing arithmetic, or yeah, you put the operator in the middle, but it turns out that there's another way that happens to be easier for certain kinds of calculations. Like I have a postfix calculator, and they're good for accounting and engineering use them. And it turns out that it's efficient for the processor to implement, or that is to evaluate, a postfix expression. So postfix expressions exist really in this class. The reason they exist is because it's easier for the machine to process these things. So yeah, so any postfix, you have the operands followed by the operator. So it's operand, operand, operator, as opposed to infix, which is operand, operator, operand. Okay, that's the difference between postfix and infix. Here I can do a more complicated one. So how about 1 times 2 plus 3, where we want to do the addition first. So we'll put parentheses on there. So in postfix, we're trying to do the addition first, so it'll be 3, 2 plus. And then this pattern of operand, operand, operator can be considered an operand. So then we want to take that operand and combine it with the operand 1 via multiplication. So this is the equivalent postfix expression for this infix. Okay, this is, humans and the machines tend to like postfix. Okay, so we need to process this string. This is a string of characters. Paren characters, ASCII characters. So we need to take it apart, and some of these things are operators and some of them are operands. So we're going to call each one of these characters a token. Okay, so a token is an operator or an operand, right? Each one of these we're just going to call a token. It's either an operator or an operand. And then we're going to use a stack to process these tokens. And as we build the postfix expression, we'll stick it into a queue. And then when we're all done, we'll take the expression out of the queue and evaluate it using a stack. Evaluate it to get the answer, which is, well, it's 2 for this guy. And then this one here was what? 2 plus 3 is 5 times 1 is 5. Okay, so here's our, well, if we were going to implement it, it might look like this, the token, that it has a value in it and the token type. So if it were an operator, like multiplication or division or parenthesis, then it would have a value 0, or a token type of 0. And if it were an operand, it's so easy to misspeak here. If it were an operand, like 2, then we'd set this value to 1 here, indicating that it's an operand. And then this value would contain the actual numeric value for an operand. So if it were 2, then this would be 1, indicating it's an operand, and this value would be 2. And if it were a paren, then this value would be 0, And the value would still contain a number, but it's just that number would be the ASCII value for a paren, whatever that is, or the ASCII value for a for an asterisk, multiply. Okay, so we got 4 kinds of operands. We've got, well, actually we've got 7. We've got multiply, divide. We've got plus and minus, and we've got parens, or left parens. And then to make the algorithm a little cleaner, we've got this hashtag, or pound sign, if you predate Twitter. And this is just to clean up the algorithm. So these two guys have a precedence of 3. These two guys have a precedence of 2. This has a precedence of 1. This has a precedence of 0. So let's look at the algorithm, and then we'll execute it. Here it is. Okay, so here it is. Let me rewrite the precedence of these dudes, because they're off the page, and it's sometimes the table's easier to see this anyway. This is our precedence. Let's do 2 plus 2, or 2 plus 2. Okay, so we got 2 plus 2, and we're trying to convert this into a 2 plus. So we want to convert this into 2 plus, which is a value of 4. All right, so we've got a stack and a queue, and so we start parsing these guys here. So we get a token, we get the 2. It's an operand, so we enqueue it. We stick it here. Then all of these else clauses are skipped, of course, because we just did the if. We did the first clause of the if here. So come back around, get the next guy. So this guy, it's not an operand, it's not a left paren, it's not a right paren. So this is what we do. We check the precedence of the token, which is 2, and the precedence at the top of the stack, which is 1. So the precedence of the token is, so the token is plus, which has a precedence of 2, and the top of the stack has a hashtag on it, which has a precedence of 1. So the precedence of the token is greater than the precedence of the top of the stack. So the loop does not execute, and we just push the token. I forgot, at the initialization you got to push this hashtag on there. I forgot to do that, so I squeezed it in, if you noticed. Okay, then we get to this dude, and that's just a operand, so we enqueue it. So we're done with this first loop here, which is, this first loop is just scanning this string. So that guy's done. So then we come down here, and this guy's just really going to clean out the stack and finish up our infix expression. So while the top of the stack is not equal to a pound, we just pop what's in the stack and enqueue it. So basically, you just move the contents of the stack onto the queue until the queue's empty. So we do that, and then it'll look like this thing here, and then we pop again, and that'll be this hashtag. So the loop will terminate, and the hashtag won't get enqueued. So this is the answer right here. Okay, that's this algorithm executing with just a simple expression with no parens. I'll do a more complicated one in a bit, but let's evaluate this guy. So now we've got the expression in the stack. the Q rather. We've got the infix expression in the Q, and we want to evaluate it to get a 4. So let's see. This was here. Let me just start over. So I've got 2 plus in a Q, and I'll start off with an empty stack, and I'll redraw the stack after every change. So I got an empty stack, and then while the Q is not empty, I DQ a token. So I'm going to take off the 2, because the DQ comes off of the left side here. And if it's an operand, it is. So I push it. There you go. Else, well, that was that. So now I DQ the next 2. It's a token. Yeah, I get it. I DQ the 2 into a token, and then that token is an operand, so I push it. So the stack looks like this now. Then we come back around and we DQ the plus sign, put that in a token. That token is an operand. That is, the else clause will go. And so what we do is we pop twice, right? We do 2 popper operations, pop, pop. And then we perform this operation here. That is, we take these 2 operands and apply the operator. So we just do 2, and then plus. So this is a function called perform that takes 2 operands and an operator and just does that operation. It returns the result. So the result will be 4. So you'll pop, use the plus sign that you just DQ'd over here to get a 4, and then push the result back on here. So that's how it works. Now you could redraw the stack after every single change, and that's the cleanest way to do it, but for this particular algorithm, it's kind of nice to do this notation, showing that you did 2 pops and then you applied the plus operation and pushed the result. So this little evaluation algorithm, that's why we like postfix, because this is a nice, clean, very fast, efficient algorithm. And think about when you write code, you write infix expressions. Why? Because that's what we're trained as humans to do. That is, our grammar for algebra is infix. That's just what, how it's been developed and how we're used to doing that. But it's more efficient to evaluate postfix. So what's the best strategy here is take your infix expressions and compile them one time into postfix. You only have to do that once when it compiles. And then every time that code runs, it's just executing postfix algorithms, which are much more efficient and cleaner and utilize the built-in, they could utilize the built-in stack in the hardware, so very fast. Okay, so that's why we like postfix expressions, because they're quick to operate, they're quick to evaluate by the machinery, and you only have to typically do that conversion from infix to postfix. You typically only have to do that once when you compile the code. All right, let's do a more complicated example, and then that'll be the end of this material here. So let's see. Let me walk through the conversion algorithm of the same thing here, and see if I can do that. Can I fit this all on here? How's that? Okay, let's do this expression here. 2 times quantity 3 plus 4 times 5. A little infix expression that you might want to write someday. This is the equivalent postfix, so we're doing the addition. That has to happen before these multiplications. So you'd want to do the addition first, then from left to right you'd do this multiplication. You'd multiply times 2, then you'd get that result and you'd multiply times 5. So what you're seeing here is the 3, 4 being added, 3, 4 plus, so this is like 1, it's going to be one quantity, you could think of it, 7. Then we're going to take that and a 2 and multiply that. So from the inside out, it's operand plus. That whole thing results into an operand, which is operand plus, times. And that whole thing turns into an operand, which would be operand times. Okay, so that's kind of thinking. It's a little bit recursive, actually. So it's related to recursion. All of this stuff in this course, we cycle back on concepts around and around. One of the things I like about this course. But anyway, the answer is 70 when you evaluate that. So let's see what this thing does. So we do a 2. It's a token, so it's a token. Everything's a token, but that token's an operand, so you enqueue it. There you go. There's the 2. Then you look at you get the times, and that's a, so it's not an operand, it's not a left paren or a right paren. So you do this, you check the precedence of the top of the stack and compare it with the precedence of your operator, yeah. So the precedence of this operator is 3, which is greater than the precedence of the top of the stack. So we don't do the loop. Instead, we push. Okay, then you get a left paren, which you just push. Okay, then you get a 3, which you just enqueue. Then you get a plus sign. So you're going to come down in here. The precedence at the top of the stack is 0 because it's got a left paren on it, and that's less. No, it's the precedence of this operator is plus, is 2, which is plus, and that's not less than the precedence of the top of the stack, which is 0. Okay, that's the hardest part to understand right here, because there's so many references through the thing. But let me do it one more time, right? So there's this plus, which has a precedence of 2. That's the precedence of the token. And then there's this left paren, which has a precedence of 0. That's this precedence at the top of the stack. 2 is not less than 0. So you skip this and you just push the token. That was the plus sign. Okay, then the 4, you enqueue that. Then the right paren, we have to do pop enqueue here. So right paren, where is it? This guy, right? This is a pop enqueue thing. When you get to a left paren, you pop the plus from the top of the stack and enqueue it until you get to until you get to a left paren. So we enqueue the plus and then we pop the left paren, which terminates a loop. Okay. Then you get to this dude over here, the multiply sign. So what is that? Is that an operator? What is this thing? So you got to do the precedence checks now. So now there's already a multiplier sitting on there, so they have the same precedence, so the loop will execute. So you're going to pop off this guy and enqueue him. And you're going to go back around and check the precedence of this, which is going to be a false in here, so the loop will stop. And then before you leave, you'll enqueue the multiply back, or you'll pop, sorry, misspoke. You'll push. Yes? So we popped off the times that's associated with this operation and queued him, and then we pushed the times that's associated with this last operation, and he's on the stack. Okay, then the 5 will get in queued. Right, the 5 will get in queued over here, and then you're done. So then this guy will come over here, will operate. This little loop here will execute, which basically just cleans out the remaining multiply sign and sticks it on here rather. Okay, so from here to here, this was the queue getting built up, and this queue contains, at this point, it contains our infix expression, or rather, our postfix expression. Sorry for the misspeaking here. It's not easy keeping all this junk straight. Anywho, that's it. So go slow and, you know, go real slow if you need to, and just do what the code says. And then redraw the stack and the queue after every change like I've done here. So the beauty of this algorithm, as I've mentioned before, is that the execution algorithm is very clean. So this execution algorithm, basically, you're going to push operands onto the stack until you get to an operator, and then when you get to an operator, you pop, eval, and then repush. That's what this says. It says read values off of the front of the queue and push them onto the stack. So the 2 will get pushed, then the 3 will get pushed, then the 4 will get pushed. Then when you get to a plus sign, you're going to pop twice. When you get to a plus sign, you're going to pop twice and then perform that operation and push the result. So you'll pop the 4 and the 3, perform the plus sign and push the result. Okay, then you'll, where are we at that point? Then the 5 will get pushed. You'll have a 5 and a 14, and then you'll pop your, you'll DQ the star, and you'll do a 5 times 14, and you know, you'll pop twice, multiply, and push the result. That's what this algorithm is saying. Okay, so classic algorithm. Let's see, before we wrap it up, you know, this is the conversion algorithm. It's kind of messy and hard to follow. You need to go real slow. But this guy here, you can go a little faster. I mean, that is to say, this is a little bit easier to understand, and that's why we have this guy, because this is an efficient algorithm that can be quickly executed, especially with a stack machine, as we call the hardware in modern computers now. We sometimes call them stack machines because they use a stack, and that support for the stack is built into the hardware, so that it's very efficient. Okay, that's stack and queue algorithms, and rounding up with this classic guy right here. Hope that was helpful to you. I'll see you next time. Bye.